Hello everyone and welcome back. In the last video, we looked into some sequences and time sequences data where we actually looked into how we can assess and address the parameters of a time series data. We have always worked with images and numbers, but we have never worked with a time series data. So, in the previous chapter 9, we looked into that time series data and what are the attributes that actually make up that data. Then, in chapter 9, we also looked into creating our own data and we plotted few plots. Now, in chapter 10, we'll be creating ML models to predict sequences. So, you created a synthetic series to use for predictions and explored how to do some basic statistical forecasting in chapter 9. And over the couple of chapters, we'll look into ML for forecasting. So before we start creating models, we need to understand how the time series data for training predictive models is used and how we actually create a windowed data set. So we'll learn more about this windowing technique and window data set in the coming chapters. So I hope you remember the synthetic time series that we saw in the previous chapter. Um, if at any point you want to predict value at time t, you will want it to predict it as a function of values preceding time t, right? So if we have already done this before, that if I want a value at time equals t, then I may want to know what were the values at time t minus 1. For example, if you want to predict the value of time series at step 1200 in the time frame given there as a function of 30 values preceding it. In this case, the values from time steps 100, 1170 to 1199 would determine the value of the time step at 1200, right? So it's kind of a window there that is used to predict the value at 1200. Right, so this is kind of the window that we'll be using forward. You can consider values from 1700, 1170 and 1199 to its features, and of course the value at 1200 would be the label. So if you get your data set into a condition where you have certain number of values as features, so the following would be the labels. So imagine that you want a value at time equals t, so that value would become a label, and preceding values till time t equals t minus 1, that those values would be actually the features, right? And before going for time series data set from chapter 9, so let's create a very basic simple data set that has all the attributes but a smaller amount of data. So here we are creating a windowed data set using tf.data libraries that contain a lot of helpful APIs for manipulating the data. And you can use these to create basic data set containing the numbers 0 to 9, emulating a time series. Right, so let's see what's the code is all about. So we use tf.data.dataset with range of 10 and the window size is 5. Shift is 1, so there will be a shift of 1 on each window. The whole window will be of 5 numbers and there'll be a shift after each loop gets over of 1, right? Then we use dataset.flat map with lambda function of window to window dot batch of 5, right? And then when we get the window, we have passed the window value, that this is the size of the window and this is the shift, and then we get the window numpy array, right? So first it creates a data set using range, simply makes the data set contain the values from 0 to n minus 1. So in this case is n is 10, so the values would be from 0 to 9. Then we call the dataset.window and pass a parameter 5 species specifies So this 5 specifies to split the data set in the windows of 5 items that I've already told you, and the shift of 1 will cause the window to shift by one spot in the from the previous one, right? So what is about the drop remainder thing? So drop underscore remainder to true specifies that once it reaches a certain point where the window won't be the same size as 5, say we reach the end of the values, and there the window size is becoming 4 rather than 5 after one shift, then it would definitely drop it over there only. It won't consider it. It will be dropped, right? So you can see in the results that you have seen here is, so you can see there are 5 numbers in each of the window, right? So there won't be a window that will be containing 6, 7, 8, 9, because there won't be any number after 9, right? But earlier you saw that we want to make training data out of this, where there are n values defining a feature and subsequent value giving a label. So what does it mean? That if I have 0, 1, 2, 3 as my uh, features, then 4 would be my label, that is the next coming value. You can do this by adding another lambda function that splits each window into everything before the last value and then the last value. So it's basic easy that you just split the values in such a way that the last value remains alone and the rest are taken as features. This gives X and Y dataset shown here. So we have added another lambda layer. Here you can see this, right? And we have split it using splicing technique, right? So the results are now that you get this. So 0, 1, 2, 3 are as one X function and 4 is a Y function. And because this data set, it also supports shuffling and batching via lambda functions. We can also shuffle and batch. So batch size would be 2. So in batches of 2, you can shuffle and batch the data set as well. So we'll see how we do that. So we use dataset dot batch of 2 dot prefetch of 1, and we pass in and we print X and Y. So you can see there are 2 values for X and simultaneously we get the 2 batches for Y as well, right? Next is, with this technique, you can turn any time series dataset into a set of training data for a neural network. So in next section, we'll explore how to take synthetic data from chapter 9 and create a training set from it, right? So creating a windowed version of time series data. Now we have a time series data and we want to create a windowed version of that. So I hope you have already seen this whole data and how we created a synthetic data set before. We have already gone through these functions of seasonal pattern, seasonality and noise, and we have taken care of the baseline, amplitude, slope and the series and how we get the series. This will create a time series that looks like in figure 10.1, right? So we'll go to figure 10.1. If you want to change it, feel free to tweak the values here and there. Then we have a function called windowed dataset that we have already seen in the previous sector. This is the same similar code and nothing much we have changed, just we have 2 lambda layers here, right? And you can use from tensor slices method of tf.data.dataset that allows you to turn a series into a dataset, right? Then we just want to give a time, split time, then we define the train time, the x train. So it's basically that the first few values would be the training and the next few, the last ones would be the validation. So it's same case for time as well as the series. Then window size of 20, batch size of 32, and you shuffle it, buffer size of 1000, and finally you get the dataset called window dataset, pass in the values, and finally the important thing to remember now is that your data is a tf.data.dataset, so it can be easily passed to model.fit as a single parameter, and tf.keras will take care of the rest. Now, if you want to inspect what the data actually looks like, you can just call dataset window data, pass in the parameters, and then just print features and labels. Here the batch size is set to 1 just to make the results more readable. Okay, so dot take of 1 is the batch size. Because the batch size is 32 that we have defined, that would be a whole lot of data. The first batch of numbers are features. We set the window size to 20. So it's a 1 cross 20 tensor, and the second number is the label, of course. So it means that these are the features, and this 67 point something, it's the label, right? So creating then training the DNN to fit. So now we have the data, we just have to use tf.fit, and first we have to define a model. So it's a basic simple dense layer model. We have 3 dense layers, and last one is 1, of course, and because we just getting the single value, and we define the input shape as the window size, and activation is relu. Simple model that you can easily use. It's compiled with loss function and optimizer as before. In this case, the loss function is specified as MSC, which stands for mean squared error, and is commonly used in regression problems. So it's basically that we have lots and lots of like a time series, and we have a number. So mean squared error works pretty good as a loss function here, right? So let's not go into that detail for that, and every data set is different, so it's good to have control. In the next section you can see how we can figure out optimal values for these as well. So just use model.compile, pass in the loss of MSC, optimizer SGD with learning rate of 1 into 10 to the power minus 6, and momentum of 0.9, and just train by calling model.fit. Right, as you train, you'll see the loss function reports number that starts high but will decline steadily. Here's the result of first 10 epochs. So you can see till 1 to 10 the loss is 47. You started pretty high, then it's dropping, and evaluating the results of DNN. Once we have trained the DNN, start predicting. But remember, you have a window data set, so the prediction for a given point is based on the values of certain number of time steps before it, right? In other words, your data is in a list called series. To predict the value, you have to pass the model values from time t to t plus the window size, and then it will give you the predicted value for the next step, right? So for example, you want to predict the value at 1020, you would take the time steps of 1000 till 1019 and use it to predict the next value of the sequence, right? Now we printed series 1000 to 1020, right? Because it takes -1, so we'll actually get the value of 1020. We print the series and then we print the value of 1020, and finally we use model.predict to check if the value printed for 1020 is exactly the same that is predicted by our model, right? So if you want to code that's a bit more generic, you can actually use these print functions for that, but I don't see any use for that right now. So you just need to note that if you are assuming a window size of 20 data points, which is small, as a result your model may lack some accuracy. So you can see that what we got was 106.25, and what our model predicted was 105.36. It's still pretty good accuracy, I would say, but it can be much more better like that, right? Since the window size was just 20. So first tensor contains the values, list of values, then we see the actual next value, that is 106.25, and finally the predicted value, right? So explore the overall prediction now. We see how good our model did. So we use forecast for that. So for time in range length of series minus the window size, we use forecast.append. We append the model.predict over the time, and we'll check how our model did, right? So first we create a new array that's called the forecast that will store the predicted values. And for every time step in the original series, you can call the predict method and store the results in the forecast array, right? You can't do this for the first n elements in the data, where n is the window size, because at that point you won't have enough data to make predictions. But after n, you can do it easily. When this loop is finished, the forecast array will have values of the predictions for time steps 21 onwards. And if you recall, you also split the dataset into training and validation sets, right? So for the next steps, you should only take the forecast from the time onwards, as your forecast data is already off by 20, right? So when we plot these whole predictions together, let's see what we get. It's a pretty good fit, I would say, right? From a quick visual inspection, the prediction does not seem too bad. It's generally following the curve of the original data. So when there are rapid changes in the data, the prediction takes a little time to catch up, but the whole thing isn't too bad for that, right? So, however, it's hard to precise your eyeballing the curve. It's best to have a good metric for that. So, we use mean absolute error to actually check how good our model is on the has trained upon. So, when we check that, the author got a value of ME to be 4.51. So, you could argue that the process of getting the predictions as accurate as possible then becomes the process of minimizing the MAE. There are some techniques that you can use to do this, including the obvious changing of window size and rest you can experiment with. Next is tuning the learning rate. As we already know that whenever we want to play with the accuracy of our model, we really look into changing the learning rate somehow so that we get attain better accuracy. So use model.compile, and then we had this code that we were using earlier for model.compile, and the learning rate was 10 into 1 into 10 to the power minus 6. And now maybe we can just use callbacks that are learning rate schedulers there. So you can actually set the values of learning rate and how much you want to vary it, if you want to increase it over the period of time, or you want to decrease it over the period of time. So these callbacks are really helpful to adjust that, right? So let's check out how we can just use a callback to adjust the learning rate parameter and plot the value of that parameter against the loss for appropriate epoch, and from there determine the best learning rate to use. So to get the callback, you just need to call tf.keras.callbacks.learning_rate_scheduler, and then you can just write learning rate scheduler equals this with the lambda function, and the epoch starts from 1 into 10 to the power minus 8 multiplied by the 10 to the power epoch by 20, right? In this case, you're going to start the learning rate at 1e minus 8, and then every epoch small increase it by small amount, right? By the time it's completed 100 epochs, the learning rate would be 1 minus e3, right? 1e minus 3, that is 10 to the power minus 3. So from 10 to the power minus 8 we went to 10 to the power minus 3, right? And when we call model.fit upon that and we check how our model actually did, for that we need to use the callbacks in the fit brackets as well. So when we call model.fit, we have to include callbacks equals learning rate schedule that we have already written before, right? So as the model.history and model.fit works, the training history is stored for you, including the loss, and you can just plot it using semi-log x. So the plot looks something like this. So it's a plot of loss versus learning rate. You can see the loss dropped while starting, and it stayed stagnant for the loss was actually going down, and then it became stagnant at the learning rate of about 10 to the power minus 7 and so on, and then it jumped right up in between somewhere 10 to the power minus 4 and 10 to the power minus 5, right? So we can say that around 10 to the power minus 3 it was the minimum value, or 10 to the power minus 5 has the smallest loss value, and that will be our new learning rate. So this is a very efficient way to actually find a optimum learning rate for your model, right? And you can see that when I measured the MAE, it tended to be 4.96. So it has taken a small step backward. And being said that, once you know your best learning rate, you can just change the number values and change the methodologies and optimize the network's performance. Next is exploring hyperparameter tuning with Keras tuner. As on the previous section, you saw how to do rough optimization of learning rate for stochastic gradient descent loss function. It certainly a very rough effort changing the learning rate every few epochs and measuring the loss. It also was somewhat tainted by the fact that loss function was already changing epoch to epoch, right? So you may not be actually finding the best value, but an approximation. To really find the best value, you have to train to the full sets of epochs with each potential value and then compare the results. And that's just one hyperparameter, the learning rate. So there are many hyperparameters that we might change to actually tune the model architecture. So let's see, fortunately there is a Keras tuner tool available that can easily get us to optimum values that can actually be helpful in tuning the model. So you just need pip install Keras tuner if you don't have it installed already, and then you can just use it as it is in the values. So you just need to figure out that what is the minimum value of your hyperparameter and what would be the maximum value and what would be the steps. So first being the number of input neurons in the model architecture. So we have like input shapes. So we change the units, the minimum values of number of neurons starting from 10 to maximum 30 neurons per layer with the step of 2, right? So this can be increased in step of 2, and instead the training the model just once to see the loss, it will train the model 11 times. So if your model is running pretty low and it's taking more time, it's just training your model 11 times, right? So then we change some optimizers, momentum. So momentum values like we were using 0.9. Now we are using a range of values starting from 0.9 to 0.7, 0.5 and 0.3, and learning rate of 10 to the power minus 5 that we have already got, and possible 4 choices that we have combined. To finish setting up, first create a function that builds the model for you. So just update the model like this. This is just the whole code that we have already seen before, with just few changes here and there. And then we call tuner random search. So that is the object that manages all the iterations of this model. So you pass and build model. Objective is loss. Maximum trials is 150. We want to get the minimum loss, right? So executions per trial is 3. And finally, we use HPs for hyperparameters used to control the values that are changing. And you just use tuner.search of dataset epochs of 100 and verbose is 0, and just get results summary based on that. Right. So once you get summary, it will give you the top 10 trials that gave the best results. Right. So you can see here, these are the results. You can see the hyperparameters. So for momentum, it goes the best value for 0.5. Units of neurons is 28. Best of all, the score is 33.18. Hyperparameters, momentum 0.7. So these are the trial summaries and how it did and what were the losses as well, right? So then you can test it again. You can just run the model with all the optimized value that you got and just put it there and run the model and then get the value. So see, it's much better than before. Slight improvement is there. So these are the things that you can use to optimize your model to get better outcomes and accuracies. So Keras Tuner is one such tool here. So I hope this whole chapter 10 was clear to you, and you can just go through the code once, and the code will be in the GitHub. The link would be in the description. And in chapter 9 and 10, we looked into time series and basic time series and machine learning with simple self-made data set that we did. And in chapter 11, we'll go beyond simple DNN and explore some recurrent neural networks that are used to predict sequential values. So thank you all for tuning in and keep learning.